Welcome to The Explainer. You know, from the factory floor to the surface of Mars, robots are pretty much everywhere. But what's the magic that actually makes them tick? Today, we're pulling back the curtain on the software brain that brings them to life. So let's start with a big question. What truly makes a machine a robot? It's easy to picture something from a sci-fi blockbuster, right? But the dream of creating an automated helper is actually ancient, woven through centuries and centuries of human history. I mean, just look at this journey. It goes way, way back. You've got Al-Jazari's incredible programmable band of musicians from the 12th century, and then Da Vinci's Mechanical Knight. The ambition was clearly there. But it wasn't until 1921 that we even got the word robot, and then another 40 years before the first real industrial robot, Unimate, started lifting hot metal on a GM assembly line. Okay, so despite that super long history and the crazy variety of robots we see today, everything from tiny surgical arms to massive Mars rovers, they all share the same three fundamental components that make them work. First up, there's the mechanical body. Think of it like the skeleton, the frame, the physical stuff. Whether it's got wheels, legs, or arms, its physical form is always designed to do a specific job, to interact with the world in a very particular way. Second, you've got the electrical system. This is kind of like the robot's power source and nervous system all rolled into one. It's the batteries, the motors, and all the sensors that give it the juice to move its body and allow it to see, hear, or feel what's going on around it. And that brings us to the real secret sauce, the programming. This is the brain. You can have the most perfectly designed body and all the power in the world, but without code, a robot is just a really expensive sculpture. The software is what tells it what to do, when to do it, and how to react to everything its sensors are picking up. Now, this whole programming thing leads to a huge challenge. If every single robot has a unique body and a unique purpose, does that mean programmers have to start from square one every single time? For a long time, the answer was basically yes, which, as you can imagine, made everything incredibly slow and super expensive. The solution that really changed the game is the Robot Operating System, or ROS. Now, the name is a little trippy because it's not a true operating system like Windows or Linux. It's better to think of it as a meta operating system. It's this flexible framework that runs on top of a normal OS, creating a common language and a standard set of tools for all sorts of different robots. And ROS totally nails that reinventing the wheel problem. Because it's open source, developers from all over the world can share and reuse code. A navigation system for one robot can be tweaked and used on another. Different parts can be written in different languages like Python or C++, and it all works together. And maybe best of all, you can test everything in a virtual simulator first. Plus, it's reliable. If one little piece of software crashes, it doesn't take the whole robot down with it. So, how does this actually work? Well, the genius of ROS is its communication system. Don't think of the robot software as one giant single program. Instead, picture it as a team of highly specialized workers who are all talking to each other through a central message board. The whole system really boils down to three core parts. First, you have the ROS master. That's the conductor or the project manager. It's the thing that lets all the other parts know who's on the team and how to find each other. Then you have the nodes. These are your specialist workers. One node might just handle the camera data. Another one just controls the wheel motors. Each one has a single specific job. And finally, you have the topics. These are the message boards where all the nodes share their info. The camera node publishes its video feed to a topic, and any other node can subscribe to that topic to get the feed. Okay, I know this might still sound a little abstract, so let's make it super concrete. We're going to walk through the most basic ROS interaction you can have, just sending a simple hello world message from one place to another. So, first you start the conductor, the master hub, with the command ROS_score. Then, in one window, you run a command that creates a temporary node that publishes the message hello world to a topic we'll call /hi. Then, in a second window, you create another node that subscribes to that exact same /hi topic. And boom, the instant the message is sent, the other node gets it and prints it to the screen. It's really that straightforward. And that basic idea, that publish and subscribe model, is the foundation for everything in ROS. By breaking a super complex robot down into all these little, independent programs that just pass messages around, developers can build, test, and fix one small piece at a time. It's an incredibly smart way to manage what would otherwise be overwhelming complexity. But you know, ROS isn't a silver bullet. It's not perfect for every single situation. Well, all that flexibility is a massive advantage. It does have a pretty steep learning curve. And because it needs a host computer to run on, like a small Raspberry Pi or something more powerful, it's not really a great fit for really tiny, low-power microrobots. So, why does all of this matter? Well, because frameworks like ROS are the software backbone for what is a truly global robotic revolution. Right now, there are an estimated 10 million industrial robots operating around the world, and that number is just growing like crazy. And these systems are the brains behind the robots that are assembling our cars, assisting in highly complex surgeries, and exploring places that are way too dangerous for humans, from deep-sea shipwrecks to the surface of another planet. The ability to build reliable robot software quickly is what makes all of this possible. And this all brings us to a final, much bigger question. As these software brains, powered by systems like ROS, get more and more sophisticated, we're shifting from building simple tools to designing incredibly complex partners. So the question isn't just, how do we build them anymore? It's, how are we going to choose to live and work right alongside them?